Welcome everybody. Today we're going to talk about solubility rules and determining precipitation reactions. But before we get into the new notes for today, I want to kind of review what we've talked about the last couple days. So hopefully you've had a chance to fill in this review section, everything that's on the first page, numbers 1 through 6. If you haven't already completed numbers 1 through 6, pause this video and answer 1 through 6, and then come back and continue watching the video. Alright, so let's go ahead and get started. So number 1 says explain what gives water its unique properties, including the ability to dissolve many solutes. So water is a polar molecule. So oxygen is more electronegative than hydrogen, therefore it pulls the electrons more so to this side of the molecule, making this side slightly negative, this side slightly positive, making it a polar compound. Another thing that determines or gives the water its unique properties is the shape. Water is a bent molecule. You'll notice that they're not seen here, but the electron pairs on oxygen are pushing down on these bonds between the oxygen and the hydrogen, causing a bent shape. Number 2, when referring to water as a great solvent, what does like dissolve like refer to? So water is a polar compound, which means it will dissolve other polar compounds. Anything that is polar and ionic will be dissolved in water because water itself is polar and ionic. So like dissolves like. Things that are polar and ionic, just like water, will be dissolved in water. Things that are nonpolar compounds like oil will not be dissolved in water because they are not the same. Number 3, which part of the water molecule would be attracted to the ions below? So when I look at a water molecule, we talked about here a second ago that oxygen is slightly negative. So oxygen in this compound is a negative atom or an anion compared to the hydrogens, which are positively charged cations. So if I've got a positively charged magnesium ion, positive is going to attract a negative because opposites attract. So magnesium is going to be attracted to the oxygen, and chlorine has a negative charge, it's an anion. Negatives are attracted to positives because, again, opposites attract. So the chlorine is going to be attracted to the hydrogen, the positive end of a water molecule. Number 4, draw a line that shows a general trend for a solid solute and a gas solute. So one of the things that we talked about previously is that as the temperature increases within a solid, the substance dissolves more readily, is more readily dissolved into that solution as the temperature increases. So solids are typically going to have a positive correlation. In other words, they're going to have a positive slope. Gases have the opposite effect. So as the temperature increases, the gas becomes less soluble in that solution, which is why the gas is shown here with a negative, a downward correlation or negative slope. Okay, so that's an easy spot. So typically things that have a positive correlation or a positive slope are going to be solids, and any lines in this graph that have a negative slope or negative correlation are going to be your gases. Let's go and slide this up a little bit here. So now I want to name the type of solutions below as saturated, unsaturated, or supersaturated. So looking at A. A says can dissolve more solute. Is that saturated, unsaturated, or supersaturated? So if I can dissolve more solute into my solution, then that solution is said to be unsaturated. B says reached equilibrium, some solute visible at the bottom. Is that saturated, unsaturated, or supersaturated? So if I've stirred and stirred and stirred and I cannot dissolve any more sugar in my tea, and some of that sugar starts to settle at the bottom of my glass, then that solution is said to be saturated. It can no longer dissolve any more solute into itself. C, dissolves more than the maximum and crystallizes easily. Is that saturated, unsaturated, or supersaturated? So if the only way that I can dissolve more than what is typically allowed is by heating up a substance, then that solution is supersaturated, meaning it's become very volatile, it's become very unstable, and the slightest disturbance can cause it to crystallize easily. So that is a supersaturated solution. D says unstable and can crystallize easily. I just mentioned that. Is that saturated, unsaturated, or supersaturated? So when more solute is dissolved into a solution by heating up that solution, we said that it becomes very unstable and it crystallizes easily. That is a supersaturated solution. E says above the line on a graph. Is that supersaturated, saturated, or unsaturated? So anything that appears above the line, so let's say this is my line right here, any value, any point value that is located above this line in this shaded region is going to be considered supersaturated, meaning it's dissolved more than it can actually handle. F says below the line on a graph. So now you're looking at this section down here. So if a point is down below a line on the graph, is that saturated, supersaturated, or unsaturated? So anything appearing below the line is going to be considered an unsaturated solution, which takes me back up here to A, meaning this solution can dissolve more solute into itself before it starts to collect at the bottom. So that is a unsaturated solution. And the last one here, G, says on the line of the graph. Is that saturated, unsaturated, or supersaturated? Anything that appears on the line itself is considered to be saturated, meaning it has reached its maximum. It cannot dissolve anymore unless you take action to increase the temperature, in which case it would be considered supersaturated. So if it's on the line, it is considered a saturated solution. So let's go ahead and look at this last part. I've got a solubility graph over here on the right. I've got some solutions. I've got sodium chlorate, I've got potassium nitrate, potassium bromide, and sodium chloride. I want to determine if, given these circumstances, if that is an unsaturated, saturated, or supersaturated for KBr, potassium bromide. So I'm only looking at potassium bromide, and I'll highlight that line right here. So I'm only looking at potassium bromide. Okay. So the first one is 60 grams at 10 degrees Celsius. Can you tell me if that's unsaturated, saturated, or supersaturated for potassium bromide, the highlighted line in this graph? So if we look over here to the right, and I find 60 grams at 10 degrees. So I'm going to zoom in a little bit on this graph. So 60 grams is about right there. Let me choose a different color. 60 grams about right there. 10 degrees, so if this is 20, 10 is right here in the middle. If I follow those points up here and there, it looks like this point, even though it's very close to the line, right here, it is technically below the line. So is that saturated, supersaturated, or unsaturated? So 60 grams at 10 degrees is an unsaturated solution because it is technically below the line. 50 grams at 10 degrees Celsius. When I find 50 grams, looks like 50 is probably right here, and 10 degrees Celsius, that is about right here. It appears as if that is also below the line. Is that supersaturated, saturated, or unsaturated? So this is again below the line. We'll call that an unsaturated solution, which means there's more room for that solute to dissolve. And the last one, 100 grams at 10 degrees Celsius. Is that saturated, unsaturated, or supersaturated? So this appears to be a supersaturated solution. And if I look, 100 grams takes me right here, and 10 degrees Celsius brings me up here. This point is above KBr. Therefore, it is a supersaturated solution. All right, so moving on, I'm going to zoom in here. What does solubility mean? So solubility is the ability of a solute to dissolve in a solvent. So it's how well does a solute dissolve in a solvent. So an example that we've looked at is, salt in water. If I pour salt in water, eventually the salt will dissolve because salt is considered soluble in water. Oil, however, is not going to dissolve in water no matter how much you stir it up or shake up the contents. It will never dissolve in water, even if I heat it up. So oil is considered insoluble. Oil is a nonpolar compound, and remember, likes dissolve likes. So if water is polar, it's only going to dissolve other polar substances. So we're going to refer to the solubility chart in our periodic table, and I posted a reference of this periodic table or this chemistry chart on Google Classroom, so I recommend that you refer back to it. I will repost it so that you know where it's at, and I'll show you here in a second. So what this solubility rules or this chart tells you is it lists all the ions that will dissolve or are soluble in water. So just to quickly show you, let's go back. Let me scoot up here a little bit. All right, so I want to determine, I've got a list of ions down here, or compounds, and I want to figure out if these compounds are soluble or insoluble in water. So I'll give you 3 steps here. Step 1 says locate the negative ion in the compound. So all of them are negative except for ammonium. Ammonium is the only one that's going to be. Okay. Step 2 says find the ion on the solubility. And then step 3 is check to see if there are any exceptions that apply to that compound. So let's practice one. Number 1 says magnesium iodide, Mgi2. So you need to figure out which is the negatively charged ion. Now, in all cases, with some exceptions, the negative ion is always going to be the second element listed, okay, or the second part of the compound that's listed if it's a polyatomic ion. So here's what I mean. So magnesium iodide, we know that magnesium is a metal. So magnesium has a positive charge. Iodide, however, is a nonmetal and it has a negative charge. So I'm only looking for the negative ion, which is iodine. So now I need to go back. In my original substance, it's bonded with magnesium. That means that magnesium iodide will dissolve in water. It is soluble, so I'll label that with an S. Let's try another one. Calcium sulfate. So you might see, well, this is calcium, there's sulfur, there's oxygen. I know calcium is metal, but sulfur and oxygen are both nonmetals. Well, you need to be able to identify your polyatomic ions as well. We've spent plenty of time practicing those. So calcium is positive. We know that it's a metal. Sulfate, SO4, this is a negatively charged polyatomic ion. So I'm only looking at sulfate. Okay? So, if we remember, calcium is not any of those. Sulfate is bonded with calcium in water in this compound. So this would be another S for soluble. So calcium sulfate is soluble. Let's move on to the next one. Sodium hydroxide. Well, we know sodium is a metal. It's got a positive charge. Hydroxide is a polyatomic ion. You have to be able to identify your polyatomic ions. And it's got a -1 charge, so this is the one that I am looking at. Okay, I'm looking at hydroxide, I looked at sulfate, I looked at iodine. So find hydroxide on your look back here. Hydroxide is bonded with sodium. Okay, it's an exception. So this is another S. Okay. Let me make a note here. Sodium is an alkali metal, so that's why it's the exception. Okay, let's look at number 4, magnesium hydroxide. So magnesium is my metal. It's listed first. It is a metal. It's a positively charged ion. OH2, this is hydroxide. This is my negatively charged ion, so this is what I'm looking at, hydroxide. It's bonded with magnesium, so is magnesium one of the exceptions? Therefore, this is an insoluble compound. All right, number 5, ammonium hydroxide. Okay, so ammonium is an ion. It's a polyatomic ion. And hydroxide is also a polyatomic ion. However, when you look up at the rules, step 1 says locate the negative ion of the compound except for ammonium. So if ammonium is part of your compound, then you're always looking for ammonium. In this case, it is. So ammonium is my ion in question. So I'm going to give ammonium an S for soluble. And the last one here is aluminum sulfide. So aluminum is not ammonium, okay, even though it's positive. Sulfur is my anion in this case, so I'm looking at sulfur. So now I need to find sulfur. Sulfur bonded with. Sulfur's bonded with aluminum, so that's another I. What portion I'm talking about? Here we go. So in your reference material, your periodic tables, we're really going to be looking at, and I'll highlight that for you, we're going to be looking at this entire section here in the middle. Okay, so we're going to be looking at solubility of common ionic compounds in water. And what you're really looking at is a list of soluble compounds, and it shows you a bunch of ions, negatively charged ions here, and it gives you some exceptions too. So we've got acetate or acetic acid, we've got ammonium, nitrate, similar to our polyatomic ions listed here. And then it'll tell you, and I'll explain this a little bit more, what some of the exceptions are. So in other words, everything that's listed right in here is soluble in water, except, and so you would have to read these exceptions to figure out what the exceptions are. So acetic acid all the way down to perchlorate have no exceptions, meaning these substances are always going to be soluble in water. However, when I get down to bromide, chloride, iodine, sulfate ions, these do have exceptions. So in other words, these ions here will always dissolve in water except when they form compounds of silver, lead, mercury, silver, lead, mercury, strontium, barium, lead, and mercury. Okay, so if any of these ions here form compounds with any of the ions listed here, then they will be considered insoluble, meaning they will not dissolve in water. Down here, I've got a list of insoluble compounds. So down here is insoluble, and up here I've got my soluble compounds, meaning these will dissolve in water except when, and these will not dissolve in water except when, so forth. So I've got carbonate, phosphate, all the way down to sulfide ions. These are always insoluble in water, except when, and then you'd have to read the exceptions. So for example, a carbonate ion is soluble in water, except when it forms compounds of ammonium and the alkali metal cation. So you need to refer to your periodic table to remember what our alkali metal cations are. Okay, positive on this chart. So you notice that all these are negative ions, negative, 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 all the way up to ammonium. Ammonium is the only one that is positive. Okay, so just something to keep in mind. So you're going to refer to this chart, and you're going to find the ion in this list. So once you have found your ion, you're going to move to the right to see if there are any exceptions to that rule. Solubility list, and I need to go down here to find iodine. Here is iodine. Okay, so iodine is soluble in water, except when it forms compounds with silver, lead, or mercury. Magnesium, silver, lead, or mercury? Well, the answer is no. It's not any of those. So it doesn't have any of those except. Go to my list, and I'm going to find sulfate. I'm going to go down the list, go down. Here's sulfate, SO4, -2 charge. So sulfate is soluble in water, except when it forms compounds with strontium, barium, lead, and mercury. Okay, so I don't see, this is not calcium, this is not calcium, not calcium, not calcium. None of these exceptions are calcium. So that means that sulfate is truly soluble. I'm going to come over here. I'm going to find hydroxide. Keep going, keep going, keep going, keep going. Here's hydroxide. Hydroxide is insoluble in water, except when it forms compounds of ammonium, the alkali metal cation, so anything in group 1, calcium, strontium, or barium. So it's got a lot of exceptions. So is sodium any of these? Sodium is not ammonium. Is it an alkali metal cation? It's not calcium, strontium, or barium. So it's not any of these. So you need to know, is sodium an alkali metal cation? Okay. Sodium is an alkali metal. So that means that even though hydroxide is insoluble, its exception is if it's bonded with an alkali metal cation. So because it's bonded with sodium, which is an alkali metal cation, it automatically turns from insoluble to soluble. Hydroxide again, we just talked about hydroxide. Here it was. It is insoluble. Now, okay, well, it says compounds of ammonium. Well, that's not magnesium. The alkali metal cations, is magnesium an alkali metal? This is calcium, strontium, barium. None of these say magnesium. So I need to know, is magnesium in group 1? So hydroxide is not bonded with an alkali metal. It's bonded with an alkaline earth metal. To my chart, I'm going to find ammonium. Here it is. It's positive. It's soluble. Does it have any exceptions? No. So that means ammonium will always be soluble. So when I come down here, look for sulfur, sulfur, sulfur. Here it is at the very bottom. So sulfur is at the bottom here. It is insoluble, which means it will not dissolve in water, except when it forms compounds of ammonium, which it didn't. Anything from the alkali metal cations, calcium, strontium, or barium. Aluminum is not ammonium. It is not in group 1. It's not calcium. It's not strontium. It's not barium. So if aluminum is not an exception, then that means anything bonded with sulfur, or aluminum in this case, bonded with sulfur, is going to be insoluble. All right. So moving on, solubility rules. I'm going to look for sulfur. Here's sulfur. Okay, sulfur is insoluble, which means it won't dissolve in water unless it forms ammonium, the alkali metal cations, calcium, strontium, or barium. Well, zinc is not any of those. Zinc is not ammonium. It's not in group 1. Zinc is not calcium, strontium, or barium. So that means zinc is not part of the exceptions. So sulfur is insoluble. Here's ammonium. It's positive. It's soluble. Has no exception. So ammonium compounds will always. I'm going to find nitrate. Here's nitrate. Nitrate is soluble, which means it will dissolve in water. Does it have any exceptions? No. So that means that when I come back over here, I'm going to find sulfate. Where's sulfate? Here it is. Sulfate is insoluble unless it is bonded with strontium, barium, lead, or mercury. Well, sulfate is bonded with barium. Barium is an exception. So that means that it is on our list. Sulfate, sulfate. Here's sulfate. Sulfate is soluble unless it is forming compounds with strontium, barium, lead, or mercury. I'm going to find nitrate. Nitrate is soluble. Does it have exceptions? Never. So let's go back. Now we're going to kind of recap what a precipitate is. So we've talked about a precipitate before. You've seen a precipitate. A precipitate is a solid powder that falls out, so to speak, of a solution. So in other words, when I mix two aqueous solutions, two solutions that are dissolved in water, so basically they are a liquid, but it's a substance dissolved in water, which technically makes it aqueous. So in other words, when two liquids combine and they form a solid, then that is a precipitate. The solid that is formed is a precipitate. So it might look like a gel, might look like some kind of a powdery substance. This right here is a precipitate that is formed when two aqueous solutions react. So how do you know, or how do you recognize the reaction? Well, precipitate reactions are always double replacement reactions. If you can remember, a double replacement reaction was a compound plus a compound produced a compound and a compound. So there were compounds on both sides of the arrow. So the reactants are both aqueous, and the products are both, aqueous and solid. Okay, so here's an example. I've got reactant AB, which is aqueous, and reactant CD, which is also aqueous. Okay, so the two reactants are both aqueous. So I can predict that my products, if a precipitate is formed, are going to be, one of them is going to be aqueous and the other one's going to be a solid. Okay, so what does this double replacement look like? So remember, the first part of this compound is going to be positive. The second part is going to be negative. This is going to be positive. This is going to be a negative. So essentially, the reactants are going to replace each other. So I've got two reactants total. In this reactant, I've got two elements. In this reactant, I've got two elements. They are going to replace each other. So positives don't bond with other positives. They bond with negatives. So this positive is going to form a bond with this negative, and this positive is going to form a bond with this negative. So what ends up happening is I get product A, D, and product C, B. Now, A, B, C, D, A, D, C, B, these are fictitious elements or compounds. So we're going to say, we said that if a precipitate is formed, one of them is going to be aqueous, the other one's going to be a solid. And the solid is going to be your precipitate, always. Okay? Alright, so the solid is the precipitate. The precipitate powder is insoluble. So the reason that it formed a solid is because it is not able to dissolve in water. It's not dissolving in that solution. Okay, so let's look a little bit further down. So we're going to practice product and identify the precipitate. Okay, here I've got my first example. Zinc nitrate, which is aqueous, so it's dissolved in water. Ammonium sulfide, also aqueous. Okay, so when I look at my compounds, zinc is a metal, it's positive. Nitrate is a polyatomic, it's negative. Ammonium is a positively charged polyatomic ion, and sulfur or sulfide is negatively charged. So they're going to each replace each other. Positives go with negatives, negatives go with positives. Like charges will not bond together. So the positive zinc is going to form a bond with the negative sulfur. And the positive ammonium is going to form a bond with the negative nitrate. Okay, so now I need to figure out, based off of the crisscross method, what the new compound will form. So I've got zinc bonding with sulfur, and I've got ammonium bonding with nitrate. So I know nitrate has a -1 charge. Ammonium has a +1 charge. When I crisscross the charges, I simply get NH4 NO3, ammonium nitrate. Okay? Zinc has a +2 charge, and the reason I know it's +2 is because in my original compound, this 2 as a subscript came from up here as a +2. So zinc has a +2 charge, and sulfur has a -2 charge. It's in group 16. So when I cross these charges, I get ZN2S2, or simply ZNS. Okay, So we use our crisscross method. Now we need to figure out which one is solid, which one is an aqueous solution. Okay, so remember, in the compound, we are only identifying the negatively charged ion. So in this case, it would be sulfur. So I'm going to go. So I know that zinc sulfide will not dissolve in water. So it is going to be a solid. Okay, which tells me that ammonium nitrate is going to be aqueous, and we'll double check that. So in ammonium nitrate, if ammonium is present, it's going to be the one in question. So I'm going to find a soluble in water, which makes it aqueous. So that means that zinc sulfide is my precipitate. Okay, so which product is the precipitate? Well, it's the one that was a solid, the one that was insoluble. It's going to be zinc sulfide. Because it's insoluble. All right, what symbol is given to the precipitate? Well, we said if it's a precipitate, then it's a solid, so it's going to have an S next to it in parentheses. All right, moving on. Let's try another example. Example, K2SO4, potassium sulfate, and barium nitrate. All right, so potassium is positive. Sulfate is a polyatomic ion, it's negative. Barium is positive. Nitrate is a polyatomic ion, it is negative. So the positive is going to form a bond with the negative. This positive is going to form a bond with this negative. So I'm going to end up with, over here, potassium and nitrate, as well as barium and sulfate. So sulfate's a polyatomic ion, and it's got a -2 charge. Barium is in group 2, so it's got a +2 charge. So when I cross these, I get Ba2SO4 or simply BaSO4. Okay, over here I've got potassium and nitrate. Nitrate's a polyatomic ion that's got a -1 charge. Potassium is an alkaline metal. It's got a +1 charge. So when I cross those, I get K1NO3 or simply KNO3. So let's figure out which one's soluble, which one's insoluble. So potassium is positive, nitrate is negative. Barium is positive, sulfate is negative. So I'm only looking for the negative ion in this compound, which is nitrate. So I need to go back. Anything bonded with nitrate is going to be soluble in water. So I'm going to give this potassium nitrate. It's going to have an AQ telling me that it is dissolved in water. Barium sulfate. So I'm only looking at the negatively charged ions, sulfate, insoluble. So that gives barium sulfate an S, which means it is a solid, which means it is my precipitate. So which product is aqueous? Well, we already determined that. It was potassium nitrate because it's soluble. Which product is the precipitate? It's the one that formed a solid, which was insoluble, which is barium sulfate. So my last example here is between potassium nitrate and magnesium sulfate. So potassium is a metal, nitrate is a polyatomic, magnesium is a metal, sulfate is a polyatomic. So the positive bonds with the negative, positive bonds with the negative, and the positive always gets listed first. So I've got potassium and sulfate. And then over here, I've got magnesium and nitrate. Okay, nitrate, we already mentioned, has a -1 charge. Magnesium has a +2 charge. So when I cross those, I get Mg, magnesium, NO3, nitrate, with a subscript of 2. Okay, over here on the left, potassium has, it's a group 1 metal, so it's got a +1 charge. Sulfate is a polyatomic with a -2 charge, so when I cross those, I get K2SO4. Now let's figure out which one is soluble and which one is not soluble. Okay, so I'm going to look at potassium as a metal, sulfate is a non-metal, it's negative, positive, negative. So remember, I'm only looking at the negative portion of this compound. So let's start with sulfate. Let's see if we can find sulfate is not bonded with any of those. It's bonded with potassium. So that means that potassium sulfate is soluble. So it's going to get AQ. It's aqueous. All right, the next one I'm going to look at is magnesium nitrate. I'm only looking at nitrate. So if it doesn't have any exceptions, it is always going to be soluble as well. So this gets AQ. Well, both of these are soluble now. This one's aqueous. Magnesium nitrate is aqueous. So that means they are both aqueous. So the question says, does this reaction form a precipitate? Well, if I've got two aqueous solutions, then both of them are soluble, meaning no precipitate will form, no reaction will take place. So hopefully you've had a chance to understand precipitate reactions and solubility rules. Hopefully you've had a chance to locate a periodic table and have one accessible. I encourage you to use your periodic table and these notes to complete the assignment for this week. So remember that everything in group 1 is an alkali metal, everything in group 2 is an alkali earth metal. So have these periodic. Well, if I look at my periodic table, here's sodium. Sodium is in group 1. These are my alkali metals. So because sodium is an alkali metal, then it is the exception. So here's magnesium. Magnesium is in group 2. These are alkali earth metals. Therefore, it is not an exception. On my list,